Okay, so for this problem, we're looking to rewrite the definite integral as a limit of Riemann sums. So the key formula for this is going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of xi times delta x. And so from this we can figure out, all right, so we know delta x is b minus a over n, and xi is a plus I times delta x. So, and we know, right, because our top bound is 6, so our b is 6, and our bottom bound is 4, so our a is going to be 4. So that is going to be 6 minus 4, which is 2, divided by n. So our delta x is going to be 2 over n. And then our xi, right, we said our a is 4. So it's going to be 4 plus our delta x is 2 over n, right? Or 2 over n times I is 2i divided by n. So our xi is going to be 4 plus 2i over n. And then we just plug this into this limit formula. So it's going to be a limit as n approaches infinity of the sum of I equals 1 to n. This part's all the same. F of xi is we literally just take f of x being the part in the parentheses here. So this is going to be 2 ln of xi being 4 plus 2i divided by n, plus 7 cube root of 4 plus 2i over n, and then all times delta x. We said our delta x is 2 divided by n, so this would be our final answer here. Okay, so now for expressing as a definite integral. So, right, there's two directions you could be asked to go with this question. Either definite integral to limit of Riemann sums or limit of Riemann sums to definite integral. So for this one, it kind of helps to first, right, we still got to identify delta x, which is still b minus a over n, and we still have to identify xi, which is still a plus I times delta x. So the delta x always sticks out. So it's usually easy to pick out because remember, if you remember the form of the other thing, like you do f of xi times delta x. So delta x is always just kind of going to be almost duct taped onto the end here, dangling like that. So it's very easy to pick out. Our delta x is going to be 2 over n. So our xi is going to be a plus I times delta x. So, but instead of using the formula to figure it out, we're going to have to pick it out. So the xi is, right, going to be a similar term. It's going to be a constant plus a term times I divided by n, or a term times n, or something like that. So if you see a term like that popping up, which usually it does more than once in these kind of problems because generally you're going to be dealing with functions with more than one x, you're going to see it pop up multiple times like this. And again, it's always like a constant plus something times I divided by something times n. So in this case, that's going to be negative 2 plus 2i over n. And our a is going to be 2, or negative 2 I should say. And our I times delta x is going to be 2i over n. So, and that makes sense, right? Because our delta x is 2 over n. So, but what this does is it allows us, so we know our a is negative 2, right? And we know our delta x is 2 over n, right? So if our delta x, right, is 2 over n, then 2 equals b minus a. So if a equals negative 2, b minus negative 2 equals equals 2, right? Because b minus a equals 2. So that's b plus 2 equals 2. So negative 2 minus, subtract 2 from both sides, so b equals 0. So right, we figure out that the width of our interval is 2, and we figure out our a, right? Our a is negative 2, and then we add our b minus a to that. So our b minus a is 2, so we add 2 to that. That's how we get that. So then our final answer is going to be this, just instead of, so right, it's going to be our function, right, again. Here, let me get a different color. So this function again, but instead of xi, we're going to use x. So every time we see negative 2 plus 2i over n, we're just going to write x instead. So it's going to be 2x cubed minus 4x plus e dx. And this would be our final answer. All right, so the next thing we're going to talk about is this integral kind of algebra almost. So you'll be given like 3 or 4 different, you'll be given a certain number of integral equalities. So it'll tell you, oh, this integral is this other integral is that, and this other integral is that, or something like that. So in these problems, and you're gonna have to find like an additional integral that you would use the other stuff to figure out, right? So there's going to be 3 main atomic operations that you're going to have to know how to do in order to solve these kinds of problems. The first one is going to be flipping. So flipping is when we have, so like for example here, right? We've got 5 to 2. In integrals, you have, right, your top bound and your bottom bound. Your top bound is B and your bottom bound is A, right? And you need your top bound to be greater than your bottom bound, right? You need your smaller number on bottom and you need your bigger number on top. If you ever run into an integral where that is not the case, like this one, you need to take a negative sign out front and then you swap the bounds. So now our larger number is on top. So that's like the first thing you should do is you should go through all of the integrals you're given and say, okay, is the bigger number on top for all of these? And if not, then you need to take a negative sign and you need to flip them. So all the other integrals, though, they seem to be okay. So we went through and we did that. All right, then the second operation you're going to need to know how to do is you're going to need to know how to subtract, and then the third one is adding, and we'll get into those now. This problem you'll be mainly doing subtraction, and the third one will be doing mainly adding. So basically how this goes is we would start with, let's start with negative 1 to 6. So we know negative 1 to 6 is 4, right? And we're looking to find 2 and 5, or from 2 to 5, right? So if we take, and here, let me color code it in highlighter. So, right, we got this, negative 1 to 6 is 4. So if we have this, and if we have negative 1 to 6, and we subtract from it negative 1 to 2, which is going to be this. If we have negative 1 to 6 and we subtract from it negative 1 to 2, then that's going to leave us with 2 to 6, right? And then if we subtract from that 5 to 6, then we're going to be left with 2 to 5. And that 5 to 6 will come from here. So, okay, so we got negative 1 to 6, which is 4. Minus negative 1 to 2, which is 6, which is negative 2. And then we subtract negative 5 from that. So negative 2 plus 5 is going to give us 3. And 3 is the answer that we're looking for, or I guess negative 3, right? Because of that negative sign out front here. So it would be a negative 3. Okay, so similarly to the last problem, the first thing you want to do is go through and you want to see if there's any integrals that need to be flipped, right? So you look at this first one, -1 to 3. An integral needs to be flipped if the bigger number is on the bottom. So, but in the case of this first integral, -1's on the bottom, that's less than 3, so we're all good there. However, for the second one, -3 is the smaller number between the two, so we're going to need to swap those. So instead of -3 on the top, it becomes -1 on the top and -3 on the bottom. And then we pick up a negative sign. So if we pick up that negative sign, this becomes a +4 instead of a -4. So, okay, and then the third one, that's fine. The smaller number is on the bottom. Perfect. Let's color code these. We'll do yellow, green, and blue. Okay. So now we need to go and we need to say, okay, we're trying to build this -3 to 3 integral. So if we take -3 to -1 and we add to it -1 to 3, then we get -3 to 3, right? So we take our yellow integral, right, -1 to 3, or sorry, our yellow integral is -1 to 3, and we take that and we add it to our green integral, which is -3 to 1. So if we add those two together, then we get our blue integral, which is -3 to 3. So then that is just going to be 4 plus 2, which is going to equal 6. So the answer you would get here would be 6. Okay, so now the last problem we're going to talk about is a problem where you're going to have to flip, you're going to have to add, you're going to have to subtract integrals. So the first thing we always do is we go through and we say, okay, does this integral need to be flipped? Does this integral need to be flipped? So starting with our first integral, right here, this one needs to be flipped, right? Because -2 is larger than -5, and -5 is currently on the top. So -2 needs to now be on the top, and -5 needs to now be on the bottom. Okay, next one, and this would become a -10 instead of a +10, right? Because we flipped the integral. Okay, so then how about this one? -5 to -4, that's okay because our smaller number is on the bottom. How about 2 to -2? That one needs to be flipped, right? 2 is the bigger number, it needs to be on top. So 2 would become on the top, -2 would become on the bottom. So then this would be a -3. Okay, then -3 to 1, so this is fine, right? The smaller number is on the bottom, so that should be okay. All right, so then we've done that, so now we need to find -4 to 2, g of x dx. Okay, so you can kind of start anywhere. Honestly, I will choose to start with this term. So here, again, I'll color code them. Okay, so if we start with our yellow integral, right, we've got -5 to -2. So and we're looking to get from -4 to 2. So if we subtract from it -5 to -4, which is our green, right? So this is yellow. This is green. So if we take our yellow and we subtract from it the green, we get -4 to -2, which gives us that -4 in the bottom bound, which is one of the bounds we want for our final answer, right? So that's cool. We definitely want to do that. So if we then take that -4 to -2 and we add -2 to 2 to that, -2 to 2, which is our blue highlighted term, then we get -4 to 2. And that is the answer we're looking for, right? -4 to 2 of g of x. So we just need to go in and fill in the numbers now. So this would be, all right, so -5 to -2 is -10, minus -4 to -5 is -2, so that would be a double negative, so that would be a +2. So, all right, so we've got -8, and now we add -3 to that, so plus a -3, would be a negative 11. So our answer would be negative 11.